Here we have a question with a piston and cylinder device, and that piston and cylinder device have a set of stops. Mass of the steam inside is 0.6 kilogram and the pressure inside is 1 megapascal. Temperature of the steam is 400 degrees Celsius. When you have a piston and cylinder device with stops, and when the piston is resting on stops, we have a constant volume process because piston cannot move further. But when the piston is not resting on stops, we have a constant pressure process. In this problem, it is said that the volume of the system when the piston is resting on stops is 40% of its initial volume. That means our piston was not resting on stops at the beginning of the process. We are asked to calculate WB. In part A, we have to calculate WB for 1 megapascal 250 degrees Celsius condition. In part B, we have to calculate WB when pressure is reduced to 500 kilopascal. And finally, we have to calculate T2 when the conditions are similar to part B. In part A, we know the final pressure is same as initial pressure, so it's a constant pressure process. And we can find boundary work using mass into pressure into volume difference. Now here I used mass because I'm going to calculate total work, not specific work. If I were to calculate specific work, I have to use P delta V. In part B, our pressure is lower than starting pressure. So we had a constant pressure process when the piston is moving towards the stops. And after we reached stops, the piston stops and it's a constant volume process. For a constant volume process, we don't have any boundary work. So we can neglect that constant work done during the constant volume process, and we can write WB is equal to WB for constant pressure process. So we can write WB is equal to MP V1 minus V2. In this case, V2 is equal to 0.4 into V1. For part C, we can calculate T2 using P1 and V2 values, P2 and V2 values, because P2 and V2 are independent intensive properties. Now let's look at part A. In here we know P1 is equal to 1 megapascal and T1 is equal to 400 degrees Celsius. Using table A5, we can see that when the pressure is 1 megapascal, saturation temperature is 179.88 degrees Celsius. So we know that our system is in superheated state, and we can calculate V1 is equal to 0.3061 cubic meters per kilogram. Similarly, we can calculate V2. Then we can find WB using our equation for boundary work. The numeric value is easy to find. How can we come up with the proper units? We know that our units are going to be kilopascals into cubic meters, but the proper units for work should be in kilojoules. So we have to get rid of pascals. I'm going to use a unity conversion ratio. We know 1 pascal is equal to 1 Newton per square meter. By multiplying by that, I can get rid of pascals, and meter cubes cancels out with meter squares, and we are left with meters now. Now I have to get rid of newtons or Newton meters. We know that 1 Newton meter is equal to 1 joule. So we get final units of kilojoules. In part B, we know that V2 is equal to V1 into 0.4. So WB is equal to 110.4 kilojoules. When it comes to finding T2 temperature, we can use P2 0.5 megapascal and V2 0.3066 into 0.4. These two values can be used to calculate T2. First, we have to decide what is the state. To find the state, we can use PV diagram. We know our pressure is 0.5 megapascal. For 0.5 megapascal, I can find VF, VG values. So VF is approximately 0.001, VG is equal to 0.19. And we can see that our V2 value falls in between these two. So this is saturated mixture. For a saturated mixture, temperature is dependent on T2. Temperature is equal to T saturation at P2. So we can find this temperature using our table A5, that is 151. Now let's talk a little bit about the system that we had, a piston and the cylinder device with stops. In our case, piston was moving towards stops. So initially pressure was constant, and when the piston reaches stops, volume becomes constant. We can have problems where the question starts with a system where piston rests on stops. In that case, initially we would have a constant volume process. When we are adding energy or removing energy from the system, things will change inside the system, and at some point pressure inside the system would be equal to the pressure from the piston. At this point, piston would start to move. So this pressure depends on the weight of the piston and pressure, etc. When the piston starts to move, we will see a process where pressure is kept constant. So remember, when the piston is resting on stops, the process is a constant volume process. When the piston is moving, process is a constant pressure process.